Cassidy to the rescue.
Cassidy's got us.
Okay? What is it?
No discrimination.
No change, no discrimination, no difference, right? There's no. Okay? Now, I told you at the beginning of the class, this is the chi-square test of independence. Okay? Which means that independence must be in your hypothesis. So this is the second exception. Okay? You can actually write a phrase here. Okay? And your phrase must include the word independence. So independence means there's no difference in admission rates. Okay? So what we're saying here, your admission rate is independent of gender, or gender is independent of admission rate, whatever. Okay? Now, the alternative, it's probably really tempting to say dependent, but don't do it. Okay? Does the admission really depend on your gender? Okay, so I'm just going to say not independent. Okay? All right, so that one's going to be a little different. So chapter 12, this is our exception chapter to the null hypothesis. Otherwise, you should put an equation there. Okay? All right, so we know it's a chi-square independence test. We now need to figure out our chi-square. So just like the last section, we're going to have the same chi-square. It's going to be the observed minus the expected squared over the expected, and of course we're going to add that up. Okay. However, the expected is going to be a little bit trickier to calculate. So here's what I would recommend that you do. I'm going to call this my observed table. Okay, this is the data I collected. Okay. So what I'm going to do is I'm going to copy that table, and I'm going to paste it, and I'm going to erase the numbers. I'm going to call this my expected table. I'm going to copy this blank table 2 times, basically. Okay. I'll call this the observed minus the expected table because I don't want to write the whole equation out there. Okay? All right. Okay, so let's talk about the expected table. Okay? So this is where it gets a little tricky, and what I'm going to do is I'm going to just give you the expected count for one cell. Okay? Now we've got a table here. And it just says row 1, column 1, row 1, column 2, row 2, column 1, row 2, column 2. Okay, so you can see that that's kind of how it's set up. Okay, so your expected count for row 1, column 1 equals your row 1 total times the column 1 total divided by your grand total. Okay? So not only do I need my column totals, as I've already figured out, but I need my row totals as well. So I'm going to go over here and I'll put totals here. I'm going to add that up. I'm going to add that up. Oh, by the way, I need to want you to pay attention on this one. Okay, notice it's adding up the row. Okay. Third one I do, it's going to add up the column. If you have a larger than 2 by 2 table, that's going to be a source of mistake. Okay, in this case it doesn't matter, but if it's a bigger than a 2 by 2, it's going to matter a lot. So pay attention to what it's highlighting here. That's a very common source of error, people not paying attention. Okay? All right, so we have 140 people that applied to this college. Okay? So here's what we're going to do. We're going to figure out the expected count here. Okay? So this is the row 1 total times the column 1 total divided by the grand total. Okay? Equals the row 1 total times the column 2 total divided by the grand total. Equals the row 2 total times the column 1 total divided by the grand total. And finally, equals row 2 total times column 2 total divided by the grand total. Okay?
What?
I tried to be as repetitive as I could there.
I'm too fast.
Okay? So, no, there aren't any cool, fast ways to do that. You're just going to have to do it manually and not make a mistake. Okay? All right, so now I've got my expected table. Okay, now let's look at this for just a moment just to make sure we're clear what's going on. So the expected table uses the assumption that admission is independent of gender. Okay, so if admission was independent of gender, we would have expected about 31.5 males to be admitted. We got 35, so more males were admitted than we would have expected. Okay, if we look over here at the females, we would have expected about 23.5 females to be admitted. We only got 20. So females were admitted at a lower rate than we would have expected. Okay? Does that make you mad, Katie? Yeah. Should. Okay? All right. So, all right, we're going to go back to our equation that we're already familiar with from last time. Okay? We're going to do the observed minus the expected squared divided by the expected. Okay? Equals the observed minus the expected squared divided by the expected equals the observed minus the expected squared divided by the expected, and finally equals the observed minus the expected squared divided by the expected. Okay? All right. So, what am I supposed to do now? Say that again? I need to find the sum, right? Okay? I'm going to add them up. What am I? So I guess that's not what I wanted to add. I want to add up that whole table, the entire table. Okay? So in this case, I get a value, a chi-squared total, equal to 1.55971. Okay? All right, what's my next step?
Wait, how did you get that sum?
How do we get that sum? I added up this whole table. Did you use parentheses? If you don't use parentheses, you'll get the wrong answer. Okay? All right, so the next step is
Find the p-value.
find the p-value, right? This is actually my chi-squared. Okay, find my p-value equals what? Chi-squared this. Now let's think about this for a minute. Which one do I need? Right tail. So as we think about this, so remember when I didn't write my null, so my null hypothesis was independent, and alternative hypothesis was not independent. Okay? So when we think about this, we're doing our chi-square distribution. If we get a small sum, what would we expect? If my sum was small, what would we expect? Would we expect there was a difference or there was not a difference? You would expect there was not a difference, right? Okay? So so over here I would say there's not a difference. If it's over here, there's going to be a big difference, right? Okay? So the idea here is, trying to decide, is 1.55 big? Okay? Thing already, right? Degrees of freedom equals rows minus 1 times columns minus 1. Okay? The independents are kind of nice and easy to figure out because they're in a table. Okay? So, how many degrees of freedom do I have in this case? 1 degree of freedom. Okay? 1 degree of freedom. So, I get a p-value equal 0.21171. Okay, now I'm going to pick on somebody that I don't pick on very often, such as Alexa. What does this p-value mean here? Does that mean reject or do not reject?
What's the difference?
We have an alpha.
What'd you say?
We have an alpha.
What's your alpha? Yeah, we didn't really specify our alpha. What's our alpha? I didn't tell you, so what did you assume? 0.05. So we're comparing our alpha with our p-value and
So we don't reject it.
do not reject. Okay? And your conclusion is what?
There is not sufficient evidence to support the claim that.
So you could say there's not evidence here, but we do not reject the null, right?
Yeah.
What does the null say?
That they are independent of gender.
So what's independent?
The admission.
The admit rate is independent of gender. And then going back to the original question, is it fair to conclude discrimination is going on?
No.
There is no discrimination going on. Okay? Women, do you believe that? Discriminated against every day, aren't you? What is this damn statistics crap? Okay? We got good evidence here, right? It's not good evidence. 43 versus 33, that's like a 10-point difference. How could we say that that's not discrimination? Well, if you're wondering that question, you're not the only one. They wondered it at Cal Berkeley too. They filed a lawsuit. And I said, okay, fine. Here's what we're going to do. We are going to go over to the engineering department because we think that the engineering department is discriminating. And we're going to tell you, give us your numbers. Okay? So the engineering department says, okay, sure, we'll give you the numbers. We had 30 men apply. We had 30 men denied. What's the admit rate? It's 50%. 30 out of 60, right? Okay? And for the women, we had 10 women apply. We had 10 women denied. What's the admit rate? 50%. Well, it's not the engineering department that's discriminating. It must be the English department. Can't trust those English majors. Okay, so the English department, they said, we have 5 men who were admitted. We had 15 who were denied. What's your admit rate? 25%. Okay? For the women, we had 10 women admitted. We had 30 that were denied. What's your admit rate? 25%. Neither department was discriminating. Okay? So this is an example of what we call Simpson's paradox. Okay? Which says that not only was there no discrimination going on, but it says if groups are unequally sized, associations can actually reverse. Now in our case, they were exactly the same. There was no discrimination going on. The problem is, as you look at this, look, over here we've got 80 people admitted, or 80 people who applied, so we've got a bigger school in engineering than we do in English, 80 versus 60. And also you can see that more men applied too, okay? So you've got unequally sized groups. And so there really was no discrimination going on. Now here's what's funny about Cal Berkeley. They filed a lawsuit and they said, we think discrimination is going on, look at your admit rate, it's terrible, okay? So they went to each department and they said, okay, engineering department, give us your numbers. The engineering department did. Guess who got the better treatment? The women. And not only that, but in every department they looked at, there was actually reverse discrimination. What they were trying to do, in the education department, it's dominated by women, right? And the nursing department, dominated by women. They wanted more men in there. So the men got better treatment. In the engineering department, in the science department, and all the other male dominated, the women got better treatment. So not only is it, in this case, they were exactly equal, but in Cal Berkeley's case, they were actually reverse, it was reverse discrimination. The women were getting better treatment in all the departments, but it was the male dominated ones that were bigger, okay? So, you can trust this hypothesis test, even when you don't want to, okay? So, any questions you guys have?
Could you go over again how you're filling each of those cells for the expected?
Sure. Okay, do you want me to erase it and we'll do it again?
Sure.
Okay. So we're using this, well, I've only given you the formula for one
Right.
cell, but it's, you know, the same applies, you just have to translate it.
Okay.
Okay, so remember you gotta use your parentheses. No, on this one you don't. Okay, so it's your row one total times your column one total divided by your grand total. Okay? Row one total times column two total divided by the grand. Row two total times column one total divided by the grand. And finally, row one total times column, row two total times column two total divided by the grand total. Okay? All right, one other thing I forgot to mention. Okay? Let's talk about some rules. I actually will thank Josh for this, because you mentioned this at the beginning of class. If 20% of your expected cells are less than 5, the test is not valid. Okay? And number 2, all counts must be greater than 1. So what I mean by that, let's say, for example, we did my expected counts here, and rather than 31, I got a value of 4. Let's pretend that I got a value of 4, that that was the correct value. How many cells do I have? Got 4 cells. One of those 4 cells is less than 5. So 25% of my cells are under 5. Okay? Notice what happened to my p-value. It got crazy. Okay? So that's a problem. The other issue is, if you have a 0 somewhere, such as here, that's a problem as well. Okay? If you have a larger table than a 2 by 2, a lot of times they will combine categories in order to get it above 5. Okay? Really, it's the expected count that matters with the 5. It's your observed where you can't have any zeros. You just cannot. If you have a 0, either combine groups to do the test, or in this case, you really couldn't do the test. Okay? And if you were comparing 0 to 43 and a half, you'd say, yeah, there's a difference. Okay? That one would be kind of obvious. Yeah, we didn't do anyone.
So when you say all counts must be greater than 1, that means all your values in your
All your
tables.
observed counts.
Okay, all observed.
Okay? All right then. So quiz is tomorrow on 12.2. Maybe we can start with
Do we need to know Simpson's paradox?
You do need to know Simpson's paradox. Okay? associations can actually reverse. In our case, they didn't necessarily reverse, they were even, but they could reverse.
That meaning that like the females could actually be.
Giving preferential treatment. Okay. Now, by the way, somebody did ask me if this applied to women in salaries. You know, Utah is one of the biggest states that has the biggest gap between salaries for men and women. Now, one of the things that I do want to point out is women often have babies when they take time off. Sometimes 20 years sometimes. Okay? So, if you actually compare a woman's experience with a man's experience, yes, there is, men are still gonna make more, but the gap is a lot smaller. Okay, when you take that into, when you take into account the time difference. So, anyway.
Gotta get Rick's rant on here.